Hi guys, I welcome you to my YouTube channel, Learn Physics with IBM. Do not forget to subscribe, do not forget to download the documents in the video description. Do not forget to share, like and comment on my videos. I'm always willing to answer any question that you, to reply to every comment that I find on my videos. I'm always trying to make my videos more easier to understand. I try my level best to make them better. So remember, we have been dealing with a series of solved past paper questions, especially AS Physics multiple choice questions 9702. We are dealing with kinematics and dynamics, and I think this is going to be part 7. So let's go. We stopped on parts in part 6. I think we stopped on a certain page. Let's go to the document. So let's go to the document so that we start from where we stopped. So in part 6, I think we stopped on page 54. So we are in part 7, we are starting on page 55. A steel sphere is dropped vertically onto a horizontal metal plate. The sphere hits the plate with speed u, leaves it with speed v, and rebounds vertically to half of its original height. Ignore air resistance. That means the acceleration due to gravity is going to be constant. Which expression gives the value of v over u? Okay, so let's think of the distance it falls through when it is going downwards. By conservation of energy, if it loses kinetic gravitational potential energy, then it should be gaining kinetic energy. So the speed with which it hits the plate will be got from a half m u squared will be, that is the gain in kinetic energy, should be equal to mgh, that is the loss in the gravitational potential energy. So from this we notice that u squared is going to be twice g times h. Then it leaves it at speed v, so it leaves with the speed v and reaches halfway. So the loss in kinetic energy when it is moving upwards is going to be a half m v squared, but it reaches halfway, so it gains gravitational potential energy, which is mg, and the height is now going to be a half times h, because the height is now half, it reaches halfway. So it means v squared is going to be mgh. Okay, so when the ratio of v over u, so I'm just going to divide these two. So v squared divided by u squared is going to be equal to mgh. Sorry, m has cancelled, m cancels here, so it is gh. M has cancelled, it is just gh. So m cancelled, so that is gh. I'm trying to remove the m. Okay, so that is going to be gh divided by twice gh. So g and h cancels to becomes a half. But remember, this side we have a square, so we have v divided by u. It's going to be the square root of 1 over 2. And the square root of 1 over 2 is the same as 1 over root of 2. So the answer is going to be C. A car of mass 500 kilograms is at rest at point X on a slope. The car's brakes are released and the car rolls down the slope with its engine switched off. At point Y, the car has moved through a vertical height of 30 meters and has a speed of 11 meters per second. What is the energy dissipated by the frictional force when the car moves from X to Y? So first of all, by conservation of energy, the loss in gravitational potential energy should be equal to the gain in kinetic energy if there was no friction. But since there is friction, then the loss in potential energy minus the gain in kinetic energy should be equal to the work done against friction. So the loss in potential energy minus the gain in kinetic energy should be equal to the work done against friction, which I'm just going to be calling work done against friction, WD. So, of course, the loss in gravitational potential energy is supposed to be mgh, and the gain in kinetic energy is going to be a half mv squared. So this difference should be equal to the work done against friction. So the work done against friction, or the work done or energy dissipated, is going to be a half, mgh, which is going to be, so this will be mgh minus a half mv squared, or the gain in kinetic energy. So the loss in gravitational potential energy is going to be the mass, which is 500 times g, which is 9.81, then times h, which is 30, minus the gain in kinetic energy. Of course, here the kinetic energy is 0, and here is going to be due to this speed, so I'll just simply say a half times the mass, which is 500, times the speed, the speed, which is 11 squared. So I'll just get this as the work done by just subtracting these two values. So this is going to be equal to, open brackets, 500 times 9.81 times 30 minus 0.5 for a half times 500 times 11 squared. I must have answered this question under work, energy, and power. So this is giving me 1.2 times 10 power 5. So that is 1.2 times 10 power 5 joules. So that is the work done against friction. So it is going to be the energy dissipated by the frictional force. So which means our answer is going to be automatically B. A rock on the surface of Mars is projected vertically upwards with an initial velocity 9 meters per second. The rock rises to a height of 12 meters above the surface. Assuming there is no atmosphere on Mars, that means there is no air resistance, what is the acceleration of free fall? So if it rises to that a height of 12 meters, that is its maximum height, at maximum height velocity is 0. If acceleration is constant, since there is no atmosphere on Mars, that means there is no air resistance. I'll use the equations of motion. So v squared is equal to u squared plus 2as. At the highest point, v is 0, so v is equal to v 0 squared is going to be initial velocity, which is 9.4 squared. If it moves against gravity, this becomes a minus 2 times g on Mars, then times 12. So what is g? I will just divide 9.4 squared divided by 2 times 12, which is 24. So that is going to be 3.7. So g is going to be 3.7 meters per second on Mars. So the answer is B. A skydiver falls from a stationary balloon at time t equals to 0. As the skydiver falls, her speed and air resistance increases. Remember, force due to air resistance is directly proportional to v squared. So that is a quadratic graph. Until the force of the air resistance is equal to her weight. At that point, acceleration is going to be 0 because the resultant force will be 0. When the force of air is equal to the weight, the resultant force is 0. Which graph best shows the variation with time t of the displacement s for the motion of the car? Of course, when acceleration is 0, v becomes constant. Since this is displacement against time, so the gradient should be a constant with time. So d is out because it's showing gradient is constant all through. So it means this is showing v is constant all through. C is wrong because it shows that v is becoming 0 here. At this point, v is 0 because the gradient is 0. B is correct because it is showing that the gradient increases at this point, which means v increases. And at this point here, it means v becomes constant. So the answer is B. A is wrong because it shows that the gradient is just increasing, which means v is just increasing indefinitely. Yet, when the weight equals the air resistance, the resultant force will be 0. The velocity becomes constant. So it becomes a straight line for a displacement time graph. So the answer is B. A ball of mass 0.2 kilograms traveling in the x direction at speed of 0.5 meters per second collides with a ball of mass 0.3 kilograms traveling the y direction at a speed of 0.4 meters per second. The balls stick together after the collision, traveling at an angle theta to the x direction. What is the value of theta? A ball of 0.2 was traveling the x direction and the other one was traveling in the y direction as shown. Then now they move at an angle. Okay. So we are going to use conservation of momentum, and I'm going to conserve momentum in the horizontal first. Conservation of momentum in the horizontal. Initially, it is only this ball which is moving in the horizontal. So total momentum in the horizontal initially is 0.2 times its speed is 0.5. This one has no momentum in the horizontal initially. Then total momentum after collision in the horizontal still, since they stick together, their total mass becomes 0.3 plus 0.2, which is 0.5, times their velocity. Let me call their velocity to be v. So it will be times v in the horizontal will be v cos of theta. So that is total momentum in the horizontal. If I conserve momentum in the vertical, this one was initially not having momentum in the vertical, so it means total momentum in the vertical was only for the other one, which is going to be 0.3 times its speed, which is 0.4. That is total momentum in the vertical. Then that is before collision. Then after collision, we resolve v in the vertical to point this side. This will be v sine of theta because this was v cos of theta. So they stick together, remember? So this becomes total mass 0.5 times their common velocity to be v sine of theta after collision. So I'll just divide the two equations. Equation 2 divided by equation 1. V cancels. So sine theta divided by cos theta is tan theta. 0.5 cancels. So on the left hand side, I have 0.3 times 0.4 divided by 0.2 times 0.5. So I'll just find theta. So theta is going to be, the ratio here is 0.3 times 0.4 divided by open brackets 0.2 times 0.5. So this is going to give us that. Then I get the tan inverse of the answer, which is 50 degrees. So this is going to be 50 degrees, which makes the answer to be C. A tennis ball is thrown horizontally in air from the top of a tall building. The effect of air resistance is not negligible. So it means if the effect of air resistance is not negligible, the acceleration decreases to 0. It decreases to 0. That means the velocity tends to a constant value. The velocity increases but becomes constant with time. What happens to the horizontal and to the vertical components of the ball's velocity? A tennis ball is thrown horizontally in air. It is thrown horizontally in air. So it means the vertical component of velocity must decrease. The horizontal component of the velocity must decrease. If it is thrown in air, it means the resultant, the air, since there is no any other force acting on the body when it is moving in the horizontal, it means the air resistance is the only force which is acting, and it acts in the opposite direction. So it means the horizontal velocity decreases to 0. So v in the x decreases to 0. But then in the vertical, v increases to terminal velocity. So in the vertical, because there is acceleration due to gravity, in the vertical, and of course the acceleration decreases in the vertical, a in the x decreases to 0 also. So velocity increases, velocity in the vertical increases to, when I write vy, that's velocity in the vertical increases to a constant value, which we shall call terminal velocity. So horizontal component of velocity, it decreases because there's air resistance, so A is out and B is also out. So it decreases because there's air resistance, but then the vertical component of velocity, because acceleration decreases, so this means this is wrong. The velocity increases but not at a constant rate. The velocity increases at a decreasing rate because the acceleration decreases, so the answer is going to be D. The rate at which the velocity increases becomes smaller until it reaches, the rate becomes 0, so the velocity becomes constant. So it increases to a maximum value, which we are going to call the terminal velocity. So if you were to sketch the graph for vertical motion, for vertical velocity, it will be like that. Water is pumped through a hose pipe at a rate of 90 kilograms per minute. Water emerges horizontally from the hose pipe with a speed of 20 meters per second. What is the minimum force required from a person holding the hose pipe to prevent it from moving backwards? So we know that force is equal to the rate of change of momentum. So change in momentum is mass times change in velocity divided by time. So the mass is 90. The velocity is going to be 20 minus 0 because initial velocity is 0. So water emerges horizontally from the hosepipe with that speed. What is the minimum force required from a person holding the hosepipe to prevent it moving backwards? So the other velocity is 0. So over the time, they gave us mass per time. So this is going to be divided by 1 minute, which is 60 seconds. So this is going to be 1/8 over 60, which I think is 30 newtons. So the answer is going to be A, 30 newtons. A ball of mass m is thrown vertically into the air. When the ball has speed v, the air resistance acting on the ball is F. What is the magnitude of the acceleration of the ball when its speed is v as it rises and as it falls? Remember, it is falling in air. So it means there will be a point where there's a point where the acceleration, okay, a ball of mass m is thrown vertically into the air. Okay, it is thrown vertically into the air. When the ball has speed v, the air resistance acting on the ball is F. So let's look at the ball when it is going upwards. So from Newton's second law, the resultant force is given by m times a. So the weight m times a is going to be equal to the weight plus f. If the ball is moving upwards, if the ball is going upwards, the weight is downwards, and the force due to air resistance is downwards. So the resultant force is equal to the weight plus the force due to air resistance. It is downwards. So this is when it is raising. So it means ma is equal to the weight, which is mg plus f. Here it is raising. It is raising upwards. So this means the acceleration is going to be equal to, if I divide by m, it will be g plus f over m. So when it is raising, the acceleration is g plus f over m. So I ignore a, I ignore b, I have c and d. Now when it is falling, if the ball is falling, the weight is downwards. So this was the direction of motion. So the weight is downwards, motion is downwards. So it means the force due to air resistance is in the opposite direction to motion. So when it is falling, the resultant force ma is going to be the weight downwards minus the air resistance upwards. But the air resistance is called F. So I'll simply say minus F. So this will be minus F. So it means acceleration is going to be, this is mg minus F. So I'm dividing by m. So m cancels. So acceleration here is going to be g minus F over m. So this means our answer is going to be C. because this was falling. What is the statement of the principle of conservation of momentum? Remember, for conservation of momentum, for a system of interacting bodies that is isolated, the total momentum is always constant. So the answer here is going to be B. In a perfectly elastic collision, the relative momentum of bodies before impact is equal to the relative momentum after impact. I think that is B. Let me check C. The momentum of a body is the product of mass and velocity. That is not a conservation of momentum. Total momentum of a system of interacting bodies remains constant provided no resultant external force acts on the system. No, the answer is D, not B. So the answer here is D. The total momentum of a system of interacting bodies remains constant provided no resultant external force acts on the system. So the answer is D, not B. That is just an error. A sprinter runs a 100-meter race. A 100-meter race, the sprinter has a constant acceleration from rest. When we see constant acceleration, equations of motion can apply. The speed then remains constant until the end of the race. Which time does it take the sprinter to run the race? Which time does it take the sprinter to run the race? Okay, remember it starts from rest, so initial velocity is going to be 0. So I'll simply use S equals to ut plus a half at squared. So the race is 100 meters, starts from rest, so this part is going to be 0. The sprinter runs a 100-meter race. The sprinter has a constant acceleration from rest of 2.5 meters until reaching a speed of 10 meters per second. Until reaching a speed of 10 meters per second. The speed then remains constant until the end of the race. Okay, the best way to do this, I'll sketch the graph. So I'll sketch a simple graph here. Speed constant, speed constant acceleration. So this is a straight line, then a horizontal line for constant speed. So it takes time t1, which I don't know, to reach a constant speed for constant acceleration. Then let this be time t2. The speed is 10. The total distance, remember, is 100 meters. Okay. So for the first one, for this part here, the distance is going to be the area under that graph. So I'll call that S1 is equal to a half times 10 times T1. Then S2 is going to be the difference between T1 and T2, then times 10. Oh, I add the distance of S1 to this one here. So this one is going to be, what is the total time? Okay, so this is going to be 10 times the time T2. The sprinter has constant acceleration. The speed then remains constant until until the end of the race. The speed is remaining constant until the end of the race. Okay. So it means where the speed is remaining constant until the end of the race, the speed is 10 meters per second. Then let the time here be t. I'll just say the time here is t. So let me use this equation first to find that. So where the acceleration is constant, the distance it travels, I'll call it S2, is equal to initial velocity. It starts with, remember, the speed then remains constant until the end of the race. So for the second part, it is 10 times the time, which I'm going to call t, or t2. For the second part, it is 10 times the time, which I'm going to call t2. For the first part, it is going to simply be a half times 80 times half times 10 t1, or you could use this equation, but for the second one, the acceleration is 2.5. You could still use this equation, which is fine. I can find t1. I can find t1. We know that acceleration is equal to 10 minus 0, since it started from rest, divided by the time t1. If I use v is equal to u plus at. So the acceleration, remember, is 2.5. So it means I get t1 as 10 divided by 2.5, which is going to be equal to 4 seconds. So the time t1 is 4 seconds. The time t1 is 4 seconds. Okay. So I'm only remaining with the time t2. So total distance, remember, is s is 100, which is going to be the distance for the first part, which is a half times 10 t1, a half times 10 t1, plus the distance of the second part, which is 10 t2. So of course t1 is now known as 4 seconds since the acceleration was known. So we only remain with the t2. I'm just substituting 100 is equal to 5 times t1, which is 4, plus 10 t2. So this is 20 minus 100, which is 80, divided by 10. So t2 is going to be 8 seconds. So t2 is 8 seconds. What time does it take the sprinter to run the race? So total time, total value of t is going to be equal to 8 plus 4, which is equal to 12 seconds. So the answer is going to be C. The resultant force of 10 newtons acts on a body for a time of 2 seconds, which graph could show the variation with the time t of the momentum p. The resultant force of 10 newtons. Remember, force is equal to the rate of change of momentum. The force is 10 newtons, so 10 newtons should be equal to the change in momentum over 2. So the difference in momentum, the change in momentum should be 20. So the change in momentum should be 20. That makes D, the change in momentum is 5. C, the change in momentum is 10. And A, the change in momentum is, A is wrong because the change in momentum is 20 minus a certain value here. So the answer is going to be B. 20 is the change in the moment. 20 should be the change in momentum. So the answer is automatically going to be B. The acceleration of free fall on the surface of planet P is 1/10 that on the surface of planet Q. On the surface of P, a body of mass 1 kilogram has a weight of that. So it means G on this surface is going to be 1 divided by 1, which is 1 Newton. G on that surface is 1 Newton per kilogram. What are the mass and weight of the same body on Q? So G on Q is going to be 1/10 of G on P. So it is 1/10 newtons per kilogram on Q. So it means the weight is going to be M times G on Q, where M remains 1. No. The acceleration of free fall on the surface of planet P is a 10th. So this one is going to be G on Q should be 10 times that of P. So this is going to be 10, not 1/10. The acceleration of free fall on planet P is a 10th. G on P is 1/10 of G on Q, which means G on Q is going to be 10 times G on P, and G on P is 1, so this is 10. So the weight here is going to be the mass, which is 1 kilogram, times G, which is 10. So the weight should be 10, not 100, not 0.1. The mass remains the same, so it is not 10. So the answer is going to be B. Two bodies traveling along the same straight line collide in a perfectly elastic collision. Which statement must be correct? Perfectly elastic. Relative speed of approach should be equal to the relative speed of separation, or the kinetic energy must be conserved. Total momentum is conserved, but total kinetic energies will reduce. That is not true. One of the bodies will be stationary. The relative speed of approach between the two bodies equals their relative speed of separation, so that is true. Relative speed of approach should be the same as relative speed of separation for the bodies to be in elastic collision, or kinetic energy is conserved. The diagram shows two identical spheres x and y. Initially, x moves with the speed v directed towards y. Y is stationary. The spheres collide elastically. If they collide elastically, relative speed of approach is v minus 0, which is v. Relative speed of separation should also be v. So let's begin by inspecting relative. So that means if the relative speed of separation is still to be v, when x collides with y, x will go to rest and y will have the speed of v. If the relative speed of separation is to be equal to the relative speed of approach, so x should stop and y moves with the speed v to the right, so that the relative speed of approach is the same as the relative speed of separation. So since they have the same mass, because they have the same mass, y cannot be stationary when x collides with it, since they have the same mass. So they just exchange the velocities because they have the same mass. You can also look at conservation of momentum first before you look at conservation of kinetic energy. So the answer is going to be D. Because they have the same mass, they just exchange their speeds. So x comes to rest as y moves with the speed v to the right. Two solid spheres have masses 2 and 4 kilograms. The spheres collide and move apart. During the collision, the 2 kilogram mass has an acceleration of 80 meters per second squared. What is the average acceleration of the 4 kilogram mass? Okay, so we know that force is equal to mass times acceleration. For the first one, it is going to be equal to, for the 2 kilogram mass is 2 times 8, which is going to be equal to 16 newtons. But by Newton's third law, F is the same. The force is going to be the same. So we shall still say 16 is equal to the mass. Now I'm looking for the 4 kilogram mass. So that is going to be 4 times its acceleration, which is not known. So the acceleration is going to be 16 divided by 4, which is going to be 4 meters per second squared. So by Newton's third law, the force is going to be the same, but the acceleration will be different because they have different masses. So the answer is going to be B. A mass is placed in a frictionless slope at 30 degrees to the horizontal. The mass is then released. What is the acceleration down the slope? The acceleration down the slope. Okay, I can sketch this. Let this angle be 30 degrees. So if the mass is there, the weight is vertically downwards. So this is B. Let this be mg. And when we resolve mg along the plane, it is mg sine theta. So it is accelerating downwards. The acceleration is in that direction. So by Newton's second law, F equals to m times a, which is going to be mg sine of theta, which is sine of 30. So the acceleration is going to be 9.81 sine of 30. So I'm dividing 9.81 by 2, 9.81 sine of 30. that is 4.905, which is 4.9. So the answer is going to be A. A parachutist falls vertically from rest at time t equals to 0 from a hot air balloon. She falls for some distance before opening the parachute. So if we are used to this question, the answer is automatically going to be A. Why? She falls for some distance, so the speed increases. She's falling in air. The speed increases until it becomes constant. This one shows a constant speed, which now increases. So this is out. Sorry, this is showing a constant acceleration, not speed. Constant acceleration, which now increases. Yet, the acceleration is going to decrease because there is air. Then the V becomes constant for some time. When it opens the parachute, the acceleration is going to increase, but in the opposite direction. So it will be negative. The gradient will be negative. So that means the speed increases in the opposite direction until again it reaches another terminal velocity where acceleration decreases to 0, and the V again becomes constant, and so on and so forth. So the answer is going to be A. The answer will be A. Acceleration decreases to 0 and V becomes constant. When you open the parachute, so here it is opening the parachute at this point here. When you open the parachute, then the acceleration increases in the opposite direction. That's why you see the gradient here is increasing. Then, after some time, so here the acceleration increases in the opposite direction. But then here, after a few minutes, you notice that the velocity is decreasing, of course. The acceleration is in the opposite direction. So we notice that with the time again, the change in velocity is becoming almost constant. So again, we are reaching terminal velocity when the parachute is now opened. Again, air resistance is equal to the weight. So the speed remains constant again. So the answer is automatically A. A ship of mass 8.4 kilograms is approaching a harbor with a speed 16.4 meters per second. By using reverse thrust, it can maintain a constant stopping force of 920 newtons. How long will it take to stop? So by Newton's second law, force is equal to mass times acceleration, which means the acceleration is going to be the force, 920,000, divided by the mass, which is 8.4 times 10 power 7. That is the acceleration. Then, since it is coming to a stop, I'll use V equals to U plus AT. To a stop, V becomes 0. It is starting from 16.4. And because it is coming to a stop, this acceleration is negative. So I'll say minus 920,000 over 8.4 times 10 power 7. So this acceleration is a deceleration. It is supposed to be negative because it is coming to a stop. Then times t. So I'll just take one quantity the other side. So I will have that t equals to 16.4 times 8.4 exponent 7 divided by 920,000, which is 1497 or 1500 seconds. And the answers are given. We don't have 1500 seconds here, but we have means. Let's check means. Divide by 60. If I divide by 60, divide this by 60 to change it to minutes, it is 25. This is 25 minutes. So the answer is going to be C. A rigid hollow sphere is immersed deep in water and released from rest. It experiences an upthrust. Which propels it towards the surface of the water. Which graph best shows the variation with time t of its upward velocity v. A rigid hollow sphere is immersed in deep water. It is immersed in deep water and released from rest. That means initial velocity should be 0. It experiences an upthrust which propels it towards the surface of the water. So it experiences an upthrust. So it means since it is in water, as the speed, it experiences an upthrust which propels it towards the surface of the water. So it is moving upwards towards the surface of the water. The weight is downwards. It means the force which opposes the motion, the dragger force, increases downwards. So it means the acceleration decreases. So as it moves upwards, the acceleration decreases. The acceleration decreases as it moves upwards. So the acceleration decreases and v must become constant. V becomes constant, so it will reach as what we call terminal velocity. So the answer is automatically A, although I skipped other multiple choice alternatives. The answer is just A. It must reach terminal velocity because as it raises upwards, the upthrust is upwards. This should be equal to the weight. With time, it will be equal to the weight plus the viscous drag as it raises, because the acceleration, this graph here, B is wrong because it shows that the acceleration remains constant throughout, yet it decreases as it raises. So the answer is going to be an aircraft initially stationary on a runway takes off with a speed of 85 kilometers per hour in a distance of no more than 1.2 kilometers. What is the minimum constant acceleration necessary for the aircraft? So if the acceleration is constant, we shall use equations of motion. So v squared is equal to u squared plus 2as. So v, I'm changing v from kilometers per hour to meters per second. So that will be 85 times 1000 divided by 3600. That's now in meters per second, but it should be squared. It starts from, it was initially stationary, so initial velocity u is 0. This will be 2 times the acceleration. And the distance it moves is 1.2 kilometers, which is 1200 meters. Okay, so I'll just find the acceleration here. 85 times 1000 divided by 3600, then divide by, sorry, this is squared, divide by 2 times 1200. So the answer is 0.23. So the acceleration is 0.23. So the answer is A. A radio-controlled toy car travels along a straight line for a time of 15 seconds. The variation with the t of the velocity v of the car is shown. What is the average velocity of the toy car for the journey shown by the graph? So to find the average velocity, we are going to find total displacement, not distance. Total displacement divided by total time taken. Remember, displacement is going to be the area under the graph. So this is the displacement here is going to be 3 times 10, which is going to be 30 meters in one direction. The displacement here is going to be, this is 6, 10 to 5, that is 5 times 6, which is going to be 30 meters. So total displacement is 0, because it is 30 minus 30. This is 30 positive, 30 negative. So 30 minus 30, that is 0, divided by 15, which is 0. So the answer here is going to be B. Total velocity is going to be 0. The acceleration of free fall on Pluto is 0.66 meters per second squared. An object weighs 6 newtons on Earth. what would the object weigh on Pluto? So we just need the mass. The weight equals to m times g. On Earth, 6 is equal to the mass times g, which is 9.81. So it means the mass is going to be equal to 6 divided by 9.81. The mass remains the same. So the weight on Pluto is going to be the mass times g, so which is 6 over 9.81 times g on Pluto, which is 0.66. So 6 times 0.66 divided by 9.81. So this is going to be 0.403 or 0.40. So the answer is going to be A. A stationary firework explodes into 3 pieces. The masses and velocities of the 3 pieces immediately after the explosion are shown. What are speeds v1 and speed v2? So it explodes. It means initial momentum is 0 because it was initially stationary. Initial momentum is 0. So I'm going to conserve momentum in, let me conserve momentum in the vertical. I'll not change the masses to grams because I know the grams will cancel out. So conserving momentum in the vertical, because in the horizontal momentum is going to be 0 after collision. In the vertical, conserving momentum, I have 50 grams, that is the mass, times its velocity in the vertical is v1 sine of 60. Then this one will also point upwards, so I'll say plus 50 grams times v2 sine of 60. Then these ones are pointing upwards. Then this one is pointing downwards. So I'll say minus. The mass is 100 grams times the velocity, which is 8. So we can't resolve 8. It is just in one plane. So because these two point upwards, I added them. Total momentum upwards. This one points downwards. Total momentum downwards. That's why I subtract. The resultant should be 0. So we try to solve. G cancels out. And therefore, I would simply say that 800 is equal to, I think sine of 60 is root 3 over 2. So I'll say 50 or root 3 over 2 times 50 v1 plus root 3 over 2 times 50 v2. So everything by 2. So I have 1,600. Oh, the 50 can cancel out. So it becomes 800 is equal to root 3 times 50. So I will have root 3 times 50 into v1 plus v2. Okay, now let's do inspection. Oh, I can even do in the vertical. This was horizontal. In the vertical, initial momentum in the vertical was 0. So this will be to the right. The other one will be to the left. To the right, is v1 cos 60. To the right is v2 cos 60. So total momentum in the horizontal, momentum after collision, initial is 0 in the horizontal. After collision, we have 50 times g times v1 cos of 60 to the left minus 50 g times v2 cos 60 to the right. So 50g cancels out, and cos of 60 also cancels out. So it means v1 is equal to v2. So v1 should be the same as v2. So we have this equation, v1 should be the same as v2. Let's first check. They're all the same. Then if v1 is the same as v2, I'll just call it v1. So I'll have that 800 is equal to root of 50 times sorry, root of 50 times 3, where there is v1 plus v2, I'll just put there twice v1 times twice v1. Something is wrong with this page. So times twice v1 so I'm just going to divide to see what v1 would be using my calculator. So this is going to be 800 divided by open brackets 2 times 3, that is 6 root of 50. 6 root 50 6 root 50. Then 800 divided by the answer. So I'm getting v1 as I think I changed this to, no, I divided this by this 2, so this is supposed to be 25, not 50. Why am I changing this? So 800 is equal to root 3 times, remember I divided 50 by 2 to become 25, so it is times 25. So I have 800 divided by root 3, then again divide by 25 by 2, which is 50. So that is 9 point something, 9.2. So V1 is 9.2. So V1, remember, should be the same as V2, so the answer is B. A projectile is thrown at an angle to the ground. At a certain time, the projectile has a horizontal velocity of that and a vertical velocity of that. What is the speed of the projectile at this time? We just find the resultant of these two. So the resultant here is by Pythagoras theorem. Resultant is going to be the square root of 23 squared plus 10.1 squared. So we'll just say 23 squared plus 10.1 squared. Then I find the square root of the answer. So V resultant is going to be 25. So the answer is 25.1. So it is 25.1. So the answer is C. The values of displacement, velocity, and acceleration of a vehicle can be deduced from graphs representing its motion. Often the areas under these graphs or the gradients of the graphs are used. What would not give a value for displacement, velocity, or an acceleration? Remember, displacement is area, velocity is gradient, acceleration is gradient from velocity time graph. So area and a velocity time graph, that gives us displacement. Gradient of displacement time graph, velocity. Gradient of velocity time graph gives us acceleration. Gradient of an acceleration time graph. What would not give a value of those? So the gradient does not give a value of any of those. So this is, the answer is D. D is not. Would not give a value of any of those. A ball is released from rest above a hard horizontal surface. The graph shows how the velocity of the bouncing ball varies with time. At which point on the graph does the ball reach its maximum height after the first bounce? So here it is the first bounce. Here the velocity increases until it hits the ground. So it bounces at this point. When it bounces, it changes direction, and now again velocity decreases in the opposite direction. So here it has reached the maximum height. At maximum height v is 0. So here it is at maximum height after the first bounce. So the answer is going to be C automatically. Here it has reached maximum height. When velocity is 0, it is at maximum height. So, but after the first bounce, the velocity with which it moves upwards is starting from B. So at maximum height, velocity becomes 0, so the answer is C. The ball is kicked upwards at an angle of 45 degrees to the horizontal ground. After a short flight, the ball returns to the ground. It may be assumed that air resistance is negligible. What is never 0? It is kicked upwards at an angle of 45 degrees. So the velocity in the horizontal will never be 0. The velocity in the horizontal does not change. It remains constant, so it's never 0. The horizontal component of the ball's acceleration, there is no acceleration, of course, in the horizontal. The horizontal component of the ball's velocity, so this one remains constant and never 0. The vertical component of the ball's momentum. Of course, velocity at the highest point is 0 in the vertical, so the vertical component becomes 0 in the vertical at the highest point. The vertical component of the ball's velocity is 0 at the highest point, so the answer is just B. The mass of a rocket-propelled truck is approximately equal to the mass of the fuel in its tank. The fuel is ignited and the truck is propelled along horizontal tracks by a constant force. The effect of air resistance is negligible, so the acceleration is constant. During a test run, the fuel is consumed at a constant rate. Which statement describes the acceleration of the truck during the test run? A. The acceleration of the truck decreases as the fuel is consumed. That is not true. Remember Newton's third law. The acceleration is actually going to increase. Burning the fuel increases the acceleration because the forward force is increased. So burning of the fuel increases the forward force by Newton's third law. It means the acceleration is going to be increased. Let's check B. The acceleration of the truck increases as the fuel is consumed, so the answer is B. I'm saying burning fuel increases the propelling force. Burning fuel increases the propelling force, and since force is equal to mass times acceleration, it also means that the acceleration increases, so the answer is B. An object is dropped at time t equals to 0 from a high building. It is dropped. That means initial velocity should be 0. Air resistance is negligible, acceleration is constant. Three graphs are plotted. The three graphs are plotted against time: the height of the object above the ground, the speed of the object, the magnitude of the resultant force on the object. Okay. Let's see. The question says what are the quantities x, y, and z? So let's go back here. It is dropped at time t equals to 0. Initial velocity is 0. Let's check the gradients. So z cannot be, initial velocity is 0. So z, because the initial velocity is 0 and they said air resistance is significant. Oh, sorry. Acceleration is not constant. Air resistance is significant. So velocity tends to a constant value when acceleration becomes 0. So the graph should become horizontal. So let's see a graph becoming horizontal is this one. So z is most likely going to be velocity. Initial velocity is 0, but because of air resistance, then the acceleration decreases. Here acceleration becomes 0. So let's see, z is speed. Z is speed. So we ignore this one and this one here. Z is speed. Okay. So if Z is speed, of course even A is going to be wrong because A is wrong. We have ignored A. D is wrong. We have B and C. Okay, let's check. What is happening to the height? One graph is for the height. Remember the object is dropped from a building, a high building. The height of the object above the ground, I think the height should be decreasing. the height should be decreasing. So it means y is going to be the height. The height should be decreasing. So, but for both graphs x and y, the height is decreasing. Okay. Then let's check the last one, the magnitude of the resultant force on the object. So what happens, since the acceleration decreases, then the force should be decreasing. And so it means the answer here is going to be C. The height of the object above the ground. Why is the height of the object above the ground? Because if this is the height, this part here, of course for both graphs, this is showing that initial velocity is 0, so it is just falling. But this is showing a decrease in, the gradient is decreasing, meaning the gradient is decreasing, but in the negative direction. The same thing applies to this, but then when we come here, it is showing that again, the change in the height reduces, yet here the height continues reducing as it tends towards 0. So the answer is automatically going to be C. So x is most likely going to be the magnitude of the resultant force on the object, that when the force remains initially constant, then it decreases because the acceleration decreases, and when the acceleration is 0, the force will tend to 0. So x is going to be 0, x is going to be force against time, and y is going to be height against time. So the answer is going to be C. The graph shows how the momentum of a motorcycle changes with time. Okay. What is the resultant force on the motorcycle? So force is the rate of change of momentum. So force will be the change in momentum over time, which is going to be 5,000 divided by time, which is 10. So that is 500 newtons. So this should be 500 newtons, which is A. A ball is set in motion at P on a frictionless surface. It moves up slope PQ along the horizontal surface QR and finally descends slope RS. It is a frictionless surface. So if P and S are on the same horizontal level, it means the work done to move to P to Q is the same as the work done along RS. So let's first eliminate some graphs. From P to Q, the first part of the graph, the speed must be decreasing. From P to Q, the speed must be decreasing. So that means we eliminate D. The speed is decreasing because it's moving against gravity, P to Q. So P to Q, V must be decreasing. Then Q to R, V must be constant because it's a horizontal surface. So we eliminate B because B is showing V decreases further. Then we now look at QS. The speed must be increasing RS, the speed must increase. And in both cases from the graph the speed is increasing. But then, so Q to S, the speed R to S, V increases. But I want you to note, of course, for both graphs, V is increasing. But remember, this is the same horizontal level, and there was no friction. So that means the work done moving up, the work done to move from P to Q should be the same as the work done to move from R to S. That means the speed at S is going to be the same as the speed at P. So it means the answer is going to be A. So since S and P on the same level, they're on the same level. And remember, there was no friction. So it means the gravitational potential energy is the same. The gravitational potential energy gained to move from P to Q should be equal to the gravitational potential energy lost to move from R to S. And remember, the loss in kinetic energy or the loss in gravitational potential energy, along Rs should be equal to the gain in kinetic energy. The loss in gravitational, since the gravitational potential energy along PQ and Rs is the same, then I'll just simply say the loss in kinetic energy along PQ, loss in KE along PQ is equal to gain in KE along Rs. So it means the final speed must be the same. So the answer is A, not C. A rubber ball is dropped onto a table and bounces back. It bounces back. The table exerts a force F on the ball. Which graph best shows the variation with time t of the force F for the short time that the ball is in contact with the table? So I think A is wrong, B is wrong. The answer is most likely going to be C, D is wrong. Why am I saying C? Okay, let's look at this before. When it just touches, this is the table, it is just touching the table. So there is a normal reaction force, the action force N1 is downwards, but then this part of the ball deforms, the part in contact deforms. So that part of the ball deforms because the force on the ball is upwards. So the contact force from the ball is upwards simply because the ball deforms. So the force is upwards. That is why just it touches. I mean, the forcing is increasing at the point of just touching. So the force must be increasing. It is not decreasing. That's why B is wrong and D is wrong. Then after, that is when it is leaving. When it is leaving, this part, the part which was deformed must be straightening up. It is now moving. It is just turning to leave. So because it is just turning to leave, it is going to move up. It is going to move upwards faster. It means the contact force from the table must decrease because it is about to leave. So it means the force from the table must decrease because the ball returns to the original shape as it is just going to leave. The ball returns to original shape. So the contact force reduces. So this part is showing the force increases when it is just in contact, and then after contact, when the ball tends to return to its shape, the force decreases. So this is the part here, force decreases here, and here it is showing the force increases. So the answer is going to be C. And lastly, for this part, a golf ball of mass M is dropped onto a hard surface from a height h1 and rebounds to a height h2. The momentum of the golf ball just as it touches the surface is different from its momentum just as it leaves the surface. What is the total change in the momentum of the golf ball between these two instants? Ignore air resistance. So remember, kinetic energy. Of course, kinetic energy is going to be momentum squared over 2m. We know that from work, energy, and power. So for the first case of the loss in kinetic energy is equal to the gain in the potential energy. So for the first case, when it is dropped onto the surface, it is losing kinetic energy, which is going to be, I will call this one P1 squared over twice m. That is the kinetic energy which is lost should be equal to the gain. The kinetic energy which is gained should be equal to the loss in potential energy, which is mg. Of course, it moves to a height h1. A golf ball of mass m is dropped onto a hard surface from a height h1. So it loses this potential energy. It loses this potential energy to gain this kinetic energy. Okay. So if I make P1 the subject, it means that P1 is going to be equal to the square root of 2m squared times g times h1, which is equal to m square root of 2g h1. Okay. Then for the second instance, of course, similarly for the second instance, and rebounds to a height h2. So now it loses kinetic energy and moves to the height h2. So the kinetic energy lost is going to be P2 squared over 2m, and the potential energy it gains is going to be mgh2, which therefore also gives us an expression of P2 as being equal to m square root of twice g, but this will be h2. But remember, this is going to be negative because it rebounds. So it is going to be negative. So what is the total change in momentum? So change in momentum, we shall subtract. It will be P1 minus P2. P1 minus P2, which is going to be m root of 2gh1 minus negative, which becomes plus m root of 2gh2. So this is the expression, and that makes the answer to be B. Okay, so that marks the end of part 7. Let part 8 start from here. So we shall start part 8 from this point. I think you learned something from this video. For any point where I made mistakes, you can always correct me. I'm bound to make mistakes, of course, because I'm human. Nevertheless, I've tried my level best to explain some things to as much as I can. So always comment, leave a question. In case you don't understand anything, I can try to give a more clarification on it. Until next time, bye bye.